The modified discrete cosine transform is a lap transform based on the type IV discrete cosine transform, with the additional property of being lapped. It is designed to be performed on consecutive blocks of a larger data set, where subsequent blocks are overlapped so that the last half of one block coincides with the first half of the next block. This overlapping, in addition to the energy compaction qualities of the DCT, makes the MDCT especially attractive for signal compression applications, since it helps to avoid artifacts stemming from the block boundaries. As a result of these advantages, the MDCT is employed in most modern lossy audio formats, including MP3, AC3, 4Bs, Windows Median Audio, ATAC, Cook, AAC, and Opus. The MDCT was proposed by Princeton, Johnson, and Bradley in 1987, following earlier work by Princeton and Bradley to develop the MDCT's underlying principle of time-domain aliasing cancellation, described below. In MP3, the MDCT is not applied to the audio signal directly, but rather to the output of a 32-band polyphase quadrature filter bank. The output of this MDCT is post-processed by an alias reduction formula to reduce the typical aliasing of the PQF filter bank. Such a combination of a filter bank with an MDCT is called a hybrid filter bank or a sub-and MDCT. AAC, on the other hand, normally uses a pure MDCT. Only the MPEG-4 variant uses a full-band PQF bank followed by an MDCT. Similar to MP3, ATAC uses stacked quadrature mirror filters followed by an MDCT. Definition: as a lap transform, the MDCT is a bit unusual compared to other Fourier-related transforms in that it has half as many outputs as inputs. In particular, it is a linear function. The two n-real numbers x0, x2 and 1 are transformed into the n-real numbers x0, x and 1 according to the formula. The normalization coefficient in front of this transform, here unity, is an arbitrary convention and differs between treatments. Only the product of the normalizations of the MDCT and the IMDCT, below, is constrained. Inverse transform equals, the inverse MDCT is known as the IMDCT. Because there are different numbers of inputs and outputs, at first glance it might seem that the MDCT should not be invertible. However, perfect invertibility is achieved by adding the overlapped IMDCTs of subsequent overlapping blocks, causing the errors to cancel and the original data to be retrieved. This technique is known as time-domain aliasing cancellation. The IMDCT transforms n-real numbers x0, xn1 into two n-real numbers y0, y2n1 according to the formula. Like for the DCT-IV, an orthogonal transform, the inverse has the same form as the Ford transform. In the case of a windowed MDCT with the usual window normalization, the normalization coefficient in front of the IMDCT should be multiplied by 2. Computation equals, although the direct application of the MDCT formula would require O, N2, operations, it is possible to compute the same thing with only O, and log n, complexity by recursively factorizing the computation, as in the fast Fourier transform. One can also compute MDCTs via other transforms, typically a DFT or a DCT, combined with O, N, pre- and post-processing steps. Also, as described below, any algorithm for the DCT-IV immediately provides a method to compute the MDCT and IMDCT of even size. Window functions: in typical signal compression applications, the transform properties are further improved by using a window function Wn that is multiplied with xn and n in the MDCT and IMDCT formulas, above, in order to avoid discontinuities at the n equals 0 and 2n boundaries by making the function go smoothly to 0 at those points. In principle, x and y could have different window functions, and the window function could also change from one block to the next, but for simplicity we consider the common case of identical window functions for equal size blocks. The transform remains invertible, for a symmetric window Wn equals W2n1n, as long as W satisfies the Princeton-Bradley condition. Various window functions are used. A window that produces a form known as a modulated lap transform is given by and is used for MP3 and MPEG-2 AAC, and for VORBs. AC3 uses a Kaiser-Bessel-derived window, and MPEG-4 AAC can also use a KBD window. Note that windows applied to the MDCT are different from windows used for some other types of signal analysis, since they must fulfill the Princeton-Bradley condition. One of the reasons for this difference is that MDCT windows are applied twice, for both the MDCT and the IMDCT. Relationship to DCT-IV and origin of TDAC, as can be seen by inspection of the definitions, for even N the MDCT is essentially equivalent to a DCT-IV, where the inputs is shifted by N/2 and two N blocks of data are transformed at once. By examining this equivalence more carefully, important properties like TDAC can be easily derived. In order to define the precise relationship to the DCT-IV, one must realize that the DCT-IV corresponds to alternating even-odd boundary conditions, even at its left boundary, odd at its right boundary, and so on. This follows from the identities and. Thus, if its inputs are an array X of length n, we can imagine extending this array to and so on, where X denotes X in reverse order. Consider an MDCT with 2 n inputs and n outputs, where we divide the inputs into 4 blocks each of size n/2. If we shift these to the right by n/2, then extend past the end of the MDCT-IV inputs, so we must fold them back according to the boundary conditions described above. Thus, the MDCT of 2 n inputs is exactly equivalent to a DCT-IV of the n inputs, where R denotes reversal as above. In this way, any algorithm to compute the DCT-IV can be trivially applied to the MDCT. Similarly, the IMDCT formula above is precisely 1/2 of the DCT-IV, where the output is extended to a length 2n and shifted back to the left by n/2. The inverse DCT-IV would simply give back the inputs from above. When this is extended via the boundary conditions and shifted, one obtains IMDCT, MDCT, A, B, C, D =/2. Half of the IMDCT outputs are thus redundant, as bar AR equals A, or BR, R, and likewise for the last two terms. If we group the inputs into bigger blocks A, B of size n, where A equals A, B, and B equals C, D, we can write this result in a simpler way, IMDCT, MDCT, A, B =/2. One can now understand how TDAC works. Suppose that one computes the MDCT of the subsequent, 50% overlapped, 2n block. The IMDCT will then yield, analogous to the above, /2. When this is added with the previous IMDCT result in the overlapping half, the reverse terms cancel and one obtains simply B, recovering the original data. Origin of TDAC equals, the origin of the term time domain aliasing cancellation is now clear. The use of input data that extend beyond the boundaries of the logical DCT-IV causes the data to be aliased in the same way that frequencies beyond the Nyquist frequency are aliased to lower frequencies, except that this aliasing occurs in the time domain instead of the frequency domain. We cannot distinguish the contributions of A and of B to the MDCT of, or equivalently, to the result of IMDCT, MDCT, A, B, C, D =/2. The combinations car doctor and so on, have precisely the right signs for the combinations to cancel when they are added. For odd n, n/2 is not an integer, so the MDCT is not simply a shift permutation of a DCT-IV. In this case, the additional shift by half a sample means that the MDCT-IMDCT becomes equivalent to the DCT-II, and the analysis is analogous to the above. Smoothness and discontinuities equals, we have seen above that the MDCT of 2n inputs is equivalent to a DCT-IV of the n inputs. The DCT-IV is designed for the case where the function at the right boundary is odd, and therefore the values near the right boundary are close to 0. If the input signal is smooth, this is the case, the rightmost components of A and B are consecutive in the input sequence, and therefore their difference is small. Let us look at the middle of the interval. If we rewrite the above expression as equals A, B, C, R, the second term, R, gives a smooth transition in the middle. However, in the first term there is a potential discontinuity where the right end of AD meets the left end of A. This is the reason for using a window function that reduces the components near the boundaries of the input sequence towards 0. Equals TDAC for the windowed MDCT equals, above. The TDAC property was proved for the ordinary MDCT, showing that adding IMDCTs of subsequent blocks in their overlapping half recovers the original data. The derivation of this inverse property for the windowed MDCT is only slightly more complicated. Consider two overlapping consecutive sets of 2n inputs and, for blocks A, B, C of size n, recall from above that when and are MDCTED, indexed, and added in their overlapping half, we obtain the original data. Now we suppose that we multiply both the MDCT inputs and the IMDCT outputs by a window function of length 2n. As above, we assume a symmetric window function, which is therefore at the form where W is a length n vector and A denotes reversal as before. Then the Prince-Bradley condition can be written as, with the squares and additions performed elementwise. Therefore, instead of indexing, we now MDCT. When this is indexed and multiplied again by the window function, the last n half becomes. Note that we no longer have the multiplication by 1/2, because the IMDCT normalization differs by a factor of 2 in the windowed case. Similarly, the windowed MDCT and IMDCT of yields, in its first n half. When we add these two halves together, we obtain recovering the original data. See also, other overlapping windowed Fourier transforms include, modulated complex lap transform, short-time Fourier transform, Welch's method. References: Enrique Smallver, Signal Processing with Lap Transforms. A. W. Johnson and A. B. Bradley, Adaptive Transform Coding Incorporating Time Domain Aliasing Cancellation, SpeechCom 6, 299-308. For algorithms, see for example, Chi-Min Liu and Wen-Chia Li, a unified fast algorithm for cosine modulated filter banks in current audio standards, J. Audio Engineering 47, 1061-1075. V. Britanak and K. R. Rao, a new fast algorithm for the unified forward and inverse MDCT-MDST computation, Signal Processing 82, 433-459, Vladimir Nikolajevic and Gerard Fetteri, computation of forward and inverse MDCT using Clenshaw's recurrence formula, i.e. trans. Sig. Proc 51, 1439-1444, J. Hong Chen, Bindar Liu, and Jafar Yang, recursive architectures for realizing modified discrete cosine transform and its inverse, i.e. trans. Circuits Syst. 2, Analog Dig. Sig. Proc 50, 38-45, J. S. Wu, H. Zedhu, L. Senhadi, and L. M. Leo, Mixed Radix algorithm for the computation of forward and inverse MDCTs, i.e. trans. Circuits Syst. I. Reg. Papers 56, 784-794, V. Britanak, A Survey of Efficient MDCT Implementations in MP3 Audio Coding Standard, Retrospective and State-of-the-Art, Signal. Process 91, 624-672, 2011. And references thereof.